Okay. Are you guys refreshed? Ready to start a new topic? Okay, so our next topic is on the second law of thermodynamics. So we've already talked a whole lot about the first law of thermodynamics, which is essentially conservation of energy. And now we're going to talk about the second law of thermodynamics. And this first part of this is kind of motivating why it exists. So we're going to do a little bit of thought experiment with this first part of the notes. All right. So we've already studied extensively that energy is a conserved process. All right, energy can't be created or destroyed, and no process can take place in violation of the first law of thermodynamics. All right, so if you're not conserving energy, it's not a thing that can happen, right? So I guess I just said that. So in order for a process to occur, it must satisfy conservation of energy. But while this is necessary, it doesn't guarantee that a process will take place. So another way to say that is just because a process conserves energy doesn't mean it's a possible process still, okay? So we need to ensure something else as well. So kind of to motivate this, we're going to do a little bit of thought experiment. So we know from experience that there's a definite direction for spontaneous processes. So a spontaneous process, just as a little bit of vocab here, this is a process that doesn't require like an input work to happen. So it's something that just happens on its own. Or it happens naturally without added W dot or Q dot. Okay, so we're not doing anything to the system. It'll just do it hands off. Okay. An example of this is if we have a cup of hot coffee left in a cooler room, eventually what happens? You end up with cool coffee, right? So the coffee cools. All right, so this is an example of a spontaneous process. We didn't add any work or heat transfer into the coffee cup. It just does this on its own, right? So this process satisfies the first law. All processes satisfy the first law, of course, right? The amount of energy lost by the coffee is equal to the amount of energy gained by the surroundings, right? So if our system is our coffee, we have that the total energy change in our coffee is equal to minus Q out. All right, so we have Q out. This is assuming a closed system, which isn't really quite right because we have steam coming out of here, but let's just imagine that we're ignoring the steam. Okay, we've contained our coffee into a tumbler like this, no steam's leaving. Okay, so and then in this circumstance, we have the temperature of the air is less than the temperature of the coffee. All right, so if our system is the coffee and the air, then we have that the change in energy of the coffee plus the change in energy of the air is equal to 0. Okay. Okay, so now in your imagination, we're going to reverse this situation. So we have hot coffee that's going to get hotter as a result of heat transfer from the cooler air. Okay. So we hopefully know from experience that this is not possible. So this process cannot take place, at least not without added work or a non-spontaneous thing going on here, right? But let's look at what conservation of energy tells us about such a circumstance, okay? So if we have T air less than T coffee, and we have Q dot in, if our system is the coffee, we have U2 minus U1 is equal to Q in. All right, and then if our system is the coffee and the surrounding air, we have that the internal energy of the coffee change plus the change in internal energy of the air is still equal to 0. So this, according to the first law of thermodynamics, this process could happen if we only considered conservation of energy. All right. So a process can occur, or this implies that the process can occur as long as the energy gained by the coffee equals the energy lost by the air. I don't know why I put a blank here. Sorry. So as long as the energy gained by the coffee is equal to the energy lost by the air, this is fine. Yes. No. So here we still have that the air is colder, but now instead of the heat transfer going from the coffee to the air, from hot to cold, it's going from cold to hot. So the coffee is getting hotter in this scenario. Does that make sense? So like if I had flipped like tea coffee is cold and tea air is hot, that'd be basically the same thing as the first one. So we know hot temperature goes from hot to cold, right? So we're gonna warm up a colder thing. So we're trying to do the opposite thing here. So we're making an already hot thing hotter, but from a colder medium. Okay. Which is like a very counterintuitive kind of thought experiment. But as long as the energy that the hot thing gains by getting hotter, as long as that's equal to the energy that's lost by the colder medium, which is the air, technically this satisfies conservation of energy, right? But we know that this can't happen, right? So is this actually possible? I think we all probably know, of course not. Let's think about another scenario, which is maybe even more ludicrous, in my opinion. So let's say that we top up our gas tank in our car and we're going to drive to the top of a mountain. On the way up the mountain, our engine is going to take in fresh air, burn fuel, and then exhaust combustion gases to the atmosphere. All right, this is how an engine works. We all expect this to happen. And let's pretend that, oh, and also our engine generates work, right? That's how the car drives, right? So we're turning our wheels, we're going up the hill. And we're losing energy in the form of heat. Okay, so this is kind of the thermodynamic event of driving a car. And then let's say that we have also timed this very perfectly so that our gas tank is empty right at the peak of our mountain. All right. Now, we're going to let our car roll down the hill to get us back to home. And we're going to gain speed because we've converted potential energy to kinetic energy. So far, so good. But then let's assume that the exhaust gases and the heat that we expelled from our engine is converted back to fuel, which is filled up in our tank by the time we get home. And then our engine or our vehicle is exhausting fresh air. So we're taking in this exhaust gas and it's condensing into fuel again. And we're breathing out fresh air from this process. Okay. The first law would state that this is indeed possible, all right? As long as our energy flows in and out are conserved, this technically would be possible according to the first law. But of course, this isn't true, right? We couldn't actually expect that this would happen, all right? So let's take a look at a couple of other spontaneous processes. All right, so what we have in this first one is we have a body at a temperature that is warmer than its surrounding air. So it is going to lose heat over time to the atmosphere until it becomes at equilibrium with its surroundings. All right, so this is essentially a hot object cooling until it reaches a thermal equilibrium. The second example is that we have pressurized air in a canister, and then it is going to start leaking out of that canister until the pressure is equalized with the atmosphere. So pressurized canister that leaks until pressure equals the atmospheric pressure. Okay. And then the last one is we have a mass that's been raised up on a pulley. We release the pulley and the mass falls to the ground. Okay. Okay. So for each of these processes, the initial state can be um, reattained or restored, but not in a spontaneous process. So in other words, we would have to put work into that bottom system to hoist the mass back up to the elevation that it was. We would need to use some kind of a pump to repressurize our canister in the middle one. And then we would need to do some kind of heat transfer to heat back up our little mass that's lost heat, right? So we would have to do something. It's not going to spontaneously go in the other direction. Okay. So what this means is that spontaneous processes can only proceed in a particular direction. So the second law of thermodynamics addresses the issue of direction of a process. All right, so essentially the issues that we had with those two thought experiments with the hot coffee getting hotter because of cold surrounding air, or the idea that we could kind of just run our car fully in reverse down a hill and get back to where we started from, all these issues are taken care of because of the direction of processes. All right, so that's what we're going to do in this unit. All right, so the use of the second law is not limited to identifying the direction of a process, but it also provides the means for establishing conditions for equilibrium. So for example, after a chemical reaction, and then it also tells us that energy has a quality as well as a quantity. Heat and work are not completely interchangeable forms of energy. And so when energy is transferred from one form to another, there is often a degradation of the supplied energy into a less useful form. Or sometimes we call this wasted energy. All right. The second law also addresses the issue of how well or efficiently energy is transformed from one form to another. And it's also used to determine the theoretical limits for the performance of commonly used engineering cycles, engines, and other devices. Okay. So the second law grounds us in reality. Okay. All right. Um, it's useful to talk about reversible and irreversible processes when we're talking about the second law. So, a spontaneous process is one in which the initial state cannot be restored uh, through. Oh, I'm sorry. No, this is the wrong word. An irreversible process. Sorry. If you're writing in pen, I apologize. So if we have an irreversible process, the initial state cannot be restored through a spontaneous process. A reversible state or a reversible process is defined as a process that can be reversed without leaving any trace on the surroundings. Or in other words, both the system as well as the surroundings are returned to their original state. Okay, as a note here, a system can be returned to its initial state following a process, regardless of whether it's reversible or irreversible. But for irreversible processes, the surroundings are generally going to be changed because they have to do some work on the system, and then they can't be returned to their initial state or original state. Okay. Another note here is that reversible processes are not actually a thing that happen. They're idealizations of actual processes. So reversible processes are not technically real. They're idealizations. Okay. Can anybody think of some sources of irreversibility? So some things that could be in a real system that would prevent you from working backwards and getting everything to its original state? I will start you off with a hint. So one is friction. All right. So these are things that essentially result in energy being converted into a lesser useful state. So friction, we end up converting energy into things like heat that's not usually useful. Other examples are heat transfer through a finite temperature difference. Unrestrained expansion of a gas or a liquid to a lower pressure. Mixing of dissimilar substances. Uh, electric current through a resistance. Spontaneous chemical reactions. And inelastic deformation. Okay. Another concept that's useful to define is that of a thermal energy reservoir. So, a thermal energy reservoir, which I will abbreviate as TER, so I don't have to write that out a bunch of times, is a sufficiently large system in stable equilibrium with a relatively large thermal energy capacity. So this is mass times the specific heat. To which or from which finite amounts of heat can be transferred without any change in temperature. All right, so some examples of reservoirs, thermal energy reservoirs would be the atmosphere, large bodies of water, large bodies of water. So things like oceans, rivers, and lakes. Industrial furnaces. And so on and so forth. All right, so we're talking very big systems that have a lot of thermal energy capacity. So if you were, for example, considering the cooling of your cup of coffee and the atmosphere is what's surrounding it, your coffee cooling isn't going to really substantially change the temperature of the atmosphere as a whole, right? Because the atmosphere is huge. Okay. So why do we need a relatively large value of MC? So if a thermal energy reservoir receives an amount of heat transfer Q during a process, its change in internal energy would be delta U is equal to Q. If the reservoir is an incompressible or an ideal gas, then we have that MC delta T is equal to Q. And therefore, delta T is equal to Q divided by MC. Right? So if we have a really large MC, that means that our change in temperature is really small. Right? Okay. So for large thermal energy capacity values, that means that delta T is small, and therefore the temperature is approximately constant. Okay, note that heat transfer from industrial sources to the environment is a major concern for environmentalists as well as engineers, as it can lead to thermal pollution. Okay. So the components that we studied in the previous topic, so nozzles, diffusers, pumps, heat exchangers, all those things are usually encountered in combination and integrated into a system rather than studied individually, right? So examples of this are steam power plants, and refrigeration cycles. So in each case, several components are linked in series, and then a working fluid is going to flow continuously through that system. And when a system at a given initial state goes through a sequence of processes and then finally returns to that initial state, the system is said to have executed a thermodynamics cycle. All right, so the energy balance for any system that's undergoing a thermodynamic cycle is going to take the form the change in energy of that cycle is equal to heat transfer for the cycle minus work for the cycle, where the change in energy is 0. All right. And so what this looks like on a PV diagram, for example, is if we start at state 1 and then we move to state 2 and then we go to state 3 and to state 4, then the last part of our process is going back to state 1. So it's a cycle because we just keep doing this over and over and over and over again, okay? Okay. So in this equation that I've written, our Q cycle is the net heat transfer for the cycle, which is the sum of Q in minus the sum of Q out over the entire cycle. All right, and the work of the cycle is also the net work for the cycle. So this is equal to the sum of the work out minus the sum of the work in over the course of the cycle. Okay. Since the cycle returns to its original state, this is equal to 0. So since E4 equals E1, then E4 minus, I'm sorry, it should be E5, essentially. So since we have E5 minus E1, that's 0. Does that make sense? So we're starting and ending at the same place, so the energy has to be the same. So in rate form, for a steady cycle, so steady cycle means that the DDT term is 0, right? We have the following. So we have Q dot of our cycle is equal to W dot of our cycle, which is the sum of the Q dot in minus the sum of all the heat transfer coming out over the course of the cycle. And that's equal to the sum of all the work dot out minus the sum of the work dot in over the course of the cycle. All right, so when you're doing these summations, it might be that for process 2 to 3, you have heat transfer in and work out. And then for process 4 to 1, you have heat transfer in and work in, and you'll have to sum up all of those Q dots and W dots as you go through the cycle, okay? This is typically kind of rearranged, this equation, to the following form. So we have the sum of the Q dot in plus W dot in for the cycle is equal to the sum of Q dot out plus the sum of W dot out for the cycle. Okay. So I've just rearranged that equation, is all that's happened. Any questions so far? Okay.